Welcome to Decoding the GRE, more specifically, Decoding GRE Math. What? You mean they don't always just ask you what they want to ask you? No, they don't. They don't just come out and say, here, solve for this. Not every time anyway. So in that sense, GRE questions aren't like the ones that you saw in math class back when you were trying to learn stuff. Back in math class, they ask you the question directly because they're trying to help you learn. But here, GRE questions are going to try to trick you. They're testing your logical process as well as whether you can kind of roll with it when the real question isn't initially evident. So as a result, students often feel like, gosh, if I get past one hurdle here, I can just solve. And our goal today is kind of helping you over that hurdle or giving you some techniques for, figuring out what the problems are actually asking. Okay. And as part of your practice, you will run into questions where the code is what stumps you. And, once you get past the code, you'll be able to solve to a solution. Whenever you run across questions like that, note what the code was that stumped you. Next time you see similar language, you're more likely to recognize it. Okay, so code is learnable through practice as well. Here's a GRE question. As such, I'm going to give somewhat standard GRE time on this one. I'll give you a minute and a half to think about it, and then we'll discuss. All right, that was about a minute and a half. And think to yourself where the code lies here. Verbalizing that to yourself is a good exercise for recognition in the future. And there's a couple things that I'd point out here. One is that the inequalities have 0 on one side, and that's true in several places in this problem, right? There's this given inequality, there's this given inequalities, and then there's the inequalities in question, right? Which answer choices are we looking at? And they all have 0 on one side. When I see that on the GRE, I rejoice, because what it means is that you don't care about the values of A and B and C. You don't care whether it's 2 or whether it's 5 or whether it's -7. What you do care about is that whether it's positive or negative. Okay, so 0 on one side of an inequality screams, what sign is it? That's one piece of code there. The other piece of code is in the phrasing of the question, which is very common. They're asking us what must be true. And that's different from what could be true. What might be true? What's occasionally true? And it suggests something about our approach. It suggests that if we plug in individual numbers, which you could certainly do, pick a number for A, B, and C, or individual numbers for A, B, and C, such that you meet the constraints given. Well, then you could find out what could be true, but how do you know that that's going to be true for any numbers that you pick? So a better way to check for what must be true is to go back to this whole thing about, I only care about the sign. because actually both of these inequalities tell us something in code. AB product is less than 0. In code, that means that it is the product, AB is the product of two numbers that have opposite signs. And look at these two examples for y. Positive times negative gives you a negative, but so does the reverse, right? Order doesn't matter. But if you had positive times positive, you'd get a positive, right? So A and B cannot have the same sign. And BC is sort of the opposite rule, in effect. That's positive, so they have the same signs. And that occurs whether they're both positive or whether they're both negative. Two negatives multiplied together cancel and make a positive. Okay, so we've got A and B are different from each other, and B and C are the same. So what we can do is put it together. All in all, we have two cases. A and B have to be different. B and C have to be the same. And so when we list them out, this is the full set of possibilities. If we plug in case 1 and case 2 and test the statements, then we know we're testing every single possibility. That's not something you would know if you plugged in just, a single set of numbers. Okay, because here we're kind of plugging for all cases at once. And from there on out, it's a matter of testing both those cases. So is AC less than 0? Yeah, you'll notice in both cases, A and C have opposite signs. So this is that same rule, right? If they have the opposite signs, the product is negative. Okay, so that's true in both cases. And it's very quick to see that B doesn't have to be negative. It is in case 1, but it fails in case 2. In other words, it's possible for B to be negative given the constraints that we have. So that's not a correct answer. And the third one is kind of neat. You can actually multiply out A's sign times B's sign squared times C's sign in both cases and find that you always get a negative. Or you could recognize that B squared, even if we hadn't listed out our cases, B squared it will always be positive. So that won't affect the sign of the overall product, and choice 3 there is really the same as choice 1. It boils down to is AC less than 0, which we've already shown is true. All right, so the code there was about sign inequalities where the signal must be true told us what to do. Take a minute and a half on this one. It's a sequence or series question. All right, so in sequence or series questions, you get this weird notation with the subscripts. Often throws people off. Here's the thing to know about the subscripts. All they tell you is what order in the list. A sequence is just a fancy list. Okay, so S sub 1 just means the first term is equal to 5 in this list. S sub 2, that means the second term is equal to 0 in this list. S sub 6 is what we're looking for. That's just the sixth term in the list. Okay, so the subscript is just the order. You will probably never do any math with that subscript, or rarely do any math with the subscript. It just tells you order in the list. You could have n as something you need to do something with. I have seen some examples of that. But in this case, no n terms appear in the definition of the sequence. The only n's we see are in the subscripts. So that tells you it's only about the order. Okay, so if you've got a list with an order you've got to keep track of, good thing to do on your paper is actually, create a place for that list to go. And since you don't know the third, fourth, and fifth terms here, just create placeholders for them. I like the idea of putting a question mark in the sixth place to keep you focused on the fact that you're solving for the sixth number. I would even recommend writing first, second, third, fourth, fifth, and sixth underneath those placeholders if you're so inclined. I like the idea of writing first and second as opposed to 1 and 2, just so you keep in mind that that's just the order, not the actual number in the list. Okay, so we've got our placeholders here. Got our first and second given terms there. And we need to figure out what are those blank terms. So for that, we turn our attention to that sequence definition. And if you're thinking about the nth term, let's say the nth term is the third term. We want to find that one anyway, so why don't we look at it? S sub 3 would be the third term. So S sub n minus 1 is S sub 2 when n is 3. So S sub 2 is the term before the third term. Right? It's the second term, it came right before it. S sub n minus 2 when n is 3 is going to be S sub 1, the first term. So that's the term before that. So for any nth term, n minus 1 term is the previous one, n minus 2 is the term before that. So don't get weirded out by plus and minus in the subscript. It just tells you, up or down from the term that you're looking at. Okay, in this case, we're going backwards because minus 1 and minus 2. And the idea behind thinking about it that way is that you should be able to put the sequence definition into words. Okay, so for every term, for this term, we're adding up the previous term, the term before that, and then subtracting 3 from it. Okay, so that's it in words. And with that, you don't really even have to reference that mathematical sequence definition anymore. You've already kind of cracked the code. And from here on out, it's just a matter of doing it. So the third term is going to be 5 plus 0 minus 3 gives you 2. So the next term, the fourth term, is going to be 0 plus 2 minus 3. At this point, be careful because you're now dealing with some negative numbers. Fifth term is going to be 2 plus minus 1. That's 2 minus 1, or just 1, but don't forget to minus 3 from it. And you end up at minus 2. And so the sixth term that we're looking for is just the sum of minus 1 and minus 2. That's minus 3. And don't forget the minus 3. So that brings you to minus 6, which is the answer. So looking back, this was a lot about decoding what the notation even meant. Subscript meant order. And from there on out, it was pretty mechanical. Just be careful about signs. People tend to make more mistakes, even with simple addition, when dealing with negative numbers than they do with positive. Highly recommended that you keep track of everything that you're doing. As simple as the math is, 5 plus 0 minus 3 equals 2, you still want to keep track of what's what and do each step separately. All right, here's a good one. For this one, I'll actually put up a timer, and I'll give you 2 minutes to think about this. All right, what is the greatest integer value of n such that 2 to the n is a factor of 200 to the 6th power? There's a lot going on here. When there's a lot going on, see if you can deal with a piece of it at a time. So let's begin with the whole greatest integer value of n such that n squared. Let's just think, what is, or 2, not n squared, 2 to the n. See how easy it is to reverse them? So what's the deal with 2 to the n if n's an integer? I always find it helps to think about what those actual numbers would be. If n is an integer, let's just look at positives. 1, 2, 3, 4, 5 for the exponent, and pretty soon you're writing down a list of the powers of 2. Okay, why didn't they just say that? What is the greatest power of 2 that is a factor of 200 to the 6th? That's what they're really asking. What does it mean for something to be a factor of another number? It means it goes into it. If you divide it in, it goes in whole amounts. So for example, 8 is a factor of 800 because it goes in 100 times. All right, so we're getting somewhere with this, but I still don't want to deal with 200 to the 6th power. That's a little daunting. So here's a technique. You can ask yourself the question, but about simpler numbers. Often doing so will reveal what's really going on. So go ahead and ask yourself this question. What's the greatest power 2 that is a factor of these numbers that I've listed here, 2, 4, 6, 80, and 100? Take a moment and think about that. Don't worry if you didn't think about all of them. Thinking about even a few would get you somewhere. So what's the greatest power of 2 that goes into 2? That's probably the most straightforward one. 2 divided by 2 gives you an integer. In other words, 2 goes in, but 4 does not go into 2. Okay, so the greatest power of 2 that goes into 2 is the first power, n equals 1. Okay, because remember, n is the exponent. It tells you which power of 2 goes in. All right, so 4, very similar. 4 goes into 4, but 8 does not. So what's the largest power of 2 that goes into 4? The second one. 4 goes in, 2 squared, n is that exponent of 2. Here's where things get interesting. Okay, if we try out 6 divided by 2, we get an integer. 2 goes in, but 4 does not. And here's where I think it's interesting. The number that I'm asking you about has gotten larger, but somehow n is not larger. N is smaller in this case. You may want to think to yourself, start thinking about why that might be. We'll keep going with this. We'll see that kind of pattern again. 80 is divisible by 16. 80 over 16 is 5, in case you're checking. But 80 divided by 32 is not an integer. So 16 goes in, that's 2 to the 4th, n is 4. And here we have another larger number, 100, divided by 4 works, but divided by 8 does not. So here we are back to n equals 2, because of 2 squared. So another reversal like that, right? Larger number, yet n is smaller. Plus, you might be thinking, this is kind of tedious. I don't want to list out numbers and, try dividing by various powers of 2 until 1 doesn't work. So let's think about why we're getting the n values that we're getting. If we look at the numbers I asked you about in their factored form, as we see over here, notice that n corresponds to the number of 2's in that factored form. Right? There are 2 2's here, n is 2. And here's where we see why 6 was not divisible by 4. There's only 1 2 in 6. We can see it in 100 as well. 100 divided by 8 failed. Why did it fail? Well, let's take a look at that as a division problem. 100 over 8 could be written this way. Both of those numbers in factored form. And look at what happens when we cancel 2's. You can cancel 2 of them out of the bottom, but you can't cancel the third one. In other words, 8 has one more 2 than 100 had. So it's stuck down there, making this a non-integer. Okay, so this fails because one of the 2's doesn't cancel. We're getting somewhere with this. What that means is when they ask us for the greatest number of 2's that you can cancel out of the bottom of this division check, they're really asking you how many 2's are in this really large number that they're asking us about. How many 2's can cancel if you had 200 to the 6th in the numerator. Okay, because notice we were putting all of the numbers we asked about in the numerator. All right, that is the code cracked, but we still have to do something with the 200 to the 6th at this point. How many 2's are in it? Well, let's find out. Still, let's look at 200 first before we worry about that exponent of 6. When you factor 200, you can do so with a tree. Count up the 2's that you get. There are 3 of them. There's actually 2 5's in the factorization as well. So you could write that in exponent form. And things are kind of easy from this point out if you remember exponent rules. But in case you don't, I've written it out. Exponents just are fancy multiplication. So 200 to the 6th is 200 times itself 6 times. So each set of parentheses is 200 there. And notice that there's 3 2's here, there's 3 2's here, there's 3 2's here, etc. There's 3 2's in 6 places. 6 sets of 3 2's. That's 18 2's all together. And that answers our question. How many 2's are there? There are 18. So notice that if you actually tried to divide this, once it's in this simplified form, you could divide it evenly by 2 to the 18th. Notice that 2 to the 18th would just cancel top and bottom. But if you tried to divide 2 to the 19th into this, 18 of the 2's would cancel and you'd be stuck with a 2 in the denominator. Okay, so 19 would fail, 18's the greatest value that works. Tough problem. So a couple good techniques there. One is, process the words in the question separately. Deal with one thing at a time. If they're asking you a question about a crazy number, ask yourself the same question about some more manageable numbers. Maybe a pattern or the code will reveal itself to you in that process. All right, switching gears a little bit, this question's all about which quantity is greater. So of course you're going to have to figure out what those quantities are and take some time to think about how you do that. So there's a lot of greater than, less than language going on here. In the choices, we see questions about which is greater, which is equal. We also see that language here, greatest integer less than something else. Oof, that's a combo. Or the least integer greater than something else. Okay, it's rare to see least and greater together. So let's start there. What does this language mean? Well, if we think about what the greatest integer less than 70 is, well, that'd just be 69. And I'm ignoring the stuff after the word that. The greatest integer less than 70 that has something that's true about it. Okay, so if we're thinking about what to do here, we'd start with 69 and see if 69 has that, something true about it. We'd test out 69 first. And if 69 didn't work, didn't have that quality that it's supposed to have, 68 would be the next thing to check. And go down from there. So if we want to look at the greatest integer less than 70 that meets a requirement, we're going to start at 69 and check the numbers in a decreasing fashion. Likewise for quantity B, if we want the least integer greater than 65, let's test out 66 first. And if that doesn't work, we'll test out 67. So that we're always trying the least integer greater than 65 that we haven't yet checked. Or that we haven't yet checked. All right, so we're going to count down on quantity A, we're going to count up on quantity B. Here's where we turn our attention to that part after the word that in quantity A. All right, so does 69 have only one factor m such that m is between 1 and 70? Well, I don't know until we factor 69. And when you do, you get 69 equals 3 times 23. Those are primes. Okay, so does it have only one factor between 1 and 70? No, it has 2. And same for 68. It has, 2 and 17. It's when we get to 67 that we get a factoring that's a little more simple. 1 times 67 is the only way to do it. So 67 is that only factor between 1 and 70. And you might start thinking about why is this? Why is this the first one that works? What makes it special? But for now, we can just say, yeah, that's the number. Okay, so quantity A is 67. Similar logic with B. Does 66 have no factor between 1 and 65? Well, we won't know until we test it. And when you do, you find 2 and 3 and 11. Okay, there's a bunch of factors between 1 and 65. 67, though, factors the same way as before, and it has no factors in that range. Again, think about what it is about 67 that makes that so. And chances are you're recognizing what's special about 67. 67 is prime. Primes only factor to 1 and themselves. And that's why primes are sort of restricted in how many factors. It happens that we see restrictive language about factors in both quantities, and 67 fit the bill both places. Both quantities are the same. So just to recap things, we've got some code already that you can start writing on your list of code or putting on flashcards. Be prepared to recognize this on future questions. Greater than or less than, where 0 is on one side, means explore the sign. Subscripts tell you what order in a sequence. Be prepared to translate sequence definitions into words. Greatest integer value of n such that 2 to the n is a factor. That's a doozy, but I guarantee the next time you see that one, you're going to say, okay, what power of 2 goes into something? Oh, I remember that's about how many 2's there were. Much easier to get to the translation if you've seen the same code at work before. All right, and we thought about greatest integer less than 70. In practical terms, that just means count up or count down. And very sneaky hidden language here about primes. Red flag for prime language in code is when they talk about how many factors there are. All right. And so this is going to be continued. As you continue with the class, you're going to see examples of GRE code at work in almost every lesson. So when you run into it, as you do problems outside of class as well, copy it down, put it on a flashcard, copy down what you realize the code was actually saying, as well as the original language. There is a code handout that you should do for homework, and you'll either, if you're in an in-person class, get that answer key in class as a result of doing that, or if you are a virtual student, you can download the solution or check in your handbook for that answer key. And don't get discouraged. Part of just, kind of getting with the program and learning how to decode things is just seeing code at work. So the first time you see it, maybe the second time you see it, it won't click with you. But if you start tracking it, the third and the fourth time, you'll be like, yep, I've seen that before. And that's the idea. Good luck.